At this point, we're going to get started. We have a lot of sparks. We'll light some fires today, and look forward to just getting started with the meat of our program. So I'd like to introduce our keynote speaker, who is Dr. Taha Kass-Haut. He is the Chief Technology Officer at GE Healthcare. GE has been a strong partner of the AIMI Center since its inception, with collaborative research projects that involve more than 40 people here at Stanford and at GE. Dr. Kass-Haut holds an MD and an MS in biostatistics from the University of Texas. He did his clinical cardiology training at Harvard's Beth Israel Deaconess Medical Center. Before he was at GE, for 5 years, he served as Vice President, Distinguished Engineer, and Chief Medical Officer at Amazon Web Services. He led Amazon Health AI strategy and efforts, including Amazon Health Lake, Amazon Comprehend Medical, and Amazon Omics. He served 2 terms under President Obama, before that as the first Chief Health Informatics Officer at the FDA, establishing Precision FDA, which is part of the Presidential Precision Medicine Initiative, and the widely accessible Open FDA that enables researchers and the public to search and analyze adverse event data. So an incredibly interesting career journey and background, and we are so delighted to have him here today to speak to us as our keynote speaker. Thank you, Dr. Kass-Haut.
Thank you very much for having me. Well, thank you so much for having me today. Really awesome to be with all of you here, and also building on the great collaboration that we've had with Stanford over the years. Let me just start really quick, just orient you about today's topics that I'd like to cover. So, first of all, I will start with advanced machine learning. I mean, at GE Healthcare, it's been in our DNA for the last decade. And then I will talk about some of the challenges and how large foundation models are going to accelerate the work that we're doing towards workflow optimization and increase that by 10x folds by reducing administrative burden and also improve diagnostic accuracy. And I'll land also with some of the work that we're doing with regulatory agencies. Advanced machine learning, deep learning, has been at the core of product development at GE Healthcare now for more than a decade. We leverage deep learning for a variety of tasks that are related to object detection, segmentation, image quality improvement, as well as reconstruction, just to name a few. One of the key innovations from last year included a program called AirX. For example, AirX Brain, which is the first anatomy-based organ slice prescription AI feature in our MRI scanners. The AI feature here allows to deliver consistent slices from the same organs for the same repeat scans for the same patient or across many patients. And it can eliminate rescan wastage as well as scan inefficiencies by ensuring that both small and large organs within the brain are aligned consistently. Sono CNS is another one that helps in the similar tasks. For example, during post-3D acquisition, by automatic detection of 4 standard views in our ultrasound, Volison fetal ultrasound images. In addition to support of the auto segmentation and consistency, this AI feature also improves sonographers' workflow by reducing the number of keystrokes by up to 80%. One thing is very important here with Volison or ultrasound is you're trying to identify 4 planes in a 3D with acquired images, which can take on average about 20 or so minutes just to do that. So the Sono CNS workflow really helps optimize that. Another key collaboration we've done also with Stanford is just this week with the 510K cleared Sonic DL, which is an MRI feature to help with the scanning of the heart by taking the accurate measurements as well as structure of the heart in one single breath, something that has been fairly troublesome for patients being in an MR machine, is trying to hold their breath several times, sometimes several minutes, just to kind of get the accurate measurements, and oftentimes repeating those. So that was one of the collaboration that we've done with Stanford, just kind of again on improving patient comfort, but also the repeatability of those images. In particular, also mentioned like in ultrasound, we have deep learning that support medical practitioners who are less experienced in sonography. And again, trying to kind of extend the care beyond, especially with shortages of ultrasound sonographers, and ultimately around how can you label organs automatically, such as the upper right quadrant, the liver, gallbladder, and right kidney, doing abdominal scans for improving quality reports. And at GE Healthcare for the last 20 years now, we've been in the care pathway for radiation therapy. And here I show the steps involved in the RT workflow. Sorry, let me just... in the RT workflow, and approximate the average of time it takes for each one of these steps. In one of the most heavy lift part of this workflow is the manual segmentations of organs at risk, or the ORs, from radiology images, which is time-consuming step in the workflow. Sometimes can take an upward of 30 hours. Sometimes it might take even several days to get all the right delineation. And we're automating the steps would clearly benefit the radiation oncologist and also for the sonometrist, trying to kind of find the right treatment, right dose for the right patient. And here to overcome these challenges, we recently received also an FDA clearance for anatomy delineation using deep learning auto-segmentation. This is a post-processing step application designed to automatically generate contours of these organs at risk from CT images. And it's intended in workflow to segment those organs and streamline the contouring process. A process that, as I mentioned, can take up to 3 hours now can be done in 15 to 20 minutes. And it's trained to have where one deep learning localization, about 15 deep learning or segmentation algorithms designed to and trained to contour about 40 different organs and sub-organs. And during this process, the DL localization model basically analyzes all the input CT images and is trained to segment those organs and then delineates the boundaries and incrementally process those in the subvolumes of the CT. And then from interoperability is spit out the DICOM images that now can be ingested directly into the radiotherapy planning software for further processing. Now, let me discuss how the foundation models and how we view those at GE Healthcare and the material investment we're making in this space is going to solve some of our challenges in scaling our approach. I started the discussion with ARX for the brain, which is automatically detect anatomy and prescribe slices. So at GE Healthcare, we started with the brain as the first anatomy, which took us about probably 2 years. Almost half of that just curating the images and then spending the second half just training the model, deploying the model, and validating the model, and then through the regulatory clearance. And as you can see here is for each of the anatomies, even with some optimization, just taking what we've learned from the brain, now trying to take that to the next set of anatomies. It took us on over a year just to develop and deploy each one of those models. So this motivated us to think really more about the direction of what we can build as a foundation model that can capture all anatomies in a single shot, and which help eliminate rescans and also scanning inefficiency. So let me go back here. As you can see here in the first one with the ARX brain, just kind of translate that to the knee and the spine and then the prostate. Each one of these is a separate journey on its own. For each one of these models requires own training. Which brings us to foundation models. There's a passage in Ernest Hemingway's novel, The Sun Also Rises, where there's a character named Mike and was asked, how did you go bankrupt? And he said, in 2 ways, he answers, gradually, then suddenly. And technological advancements happen much of the same way. where small changes accumulate and then suddenly the world is in a different place. I mean, this is what we've seen just in the last few months with large foundation models, which is great as we see this as an inflection point that where we've seen this rapid and dramatic technology and its effect on society in all its segments. I mean, large generative AI models or large foundation models, I mean, is how we can create and visualize new content, communicate, and even work efficiently. They will likely impact societies from business development to medicine, from education to research and even art, and from coding, even coding software. And at high level, I mean, these are models trained on a large amount of data in a self-supervised manner without any manual labels. And these models can generate to generalize to tasks and data distributions beyond what they already have seen. They are capable of creating new content, combining inputs from various examples, just like how humans make reasoning from prior experiences. So currently we're working on many domain-specific AI models, which is great for our business, but while they meet our business needs, I mean, this approach is really not scalable for what we're trying to do at GE Healthcare. I mean, we have 4 million installs, touching 1 billion patients, pretty much every modality you can imagine in imaging and ultrasound and even monitoring. So, for example, we have to develop separate models for each one of the AirX and restarting the model development step from scratch every time. And despite the recent sort of progress in the field of medical AI and most existing models have the features of they're fairly narrow and single task systems that require large quantities of highly curated, high quality data to train, and these models cannot easily be reused to new clinical context, as they often require collection, de-identification, as well as annotation of site-specific data for every new deployment, which is both laborious and expensive. So instead of proceeding this way, for these and other use cases, I mean, it would be advantageous to, I mean, first leverage the all acquired healthcare data to learn the overall healthcare-specific domain, then genetic data to learn the AI domain, and then fill out the gaps with any gaps with knowledge-based synthetic data. I mean, leveraging such large-scale genetic models called foundation models, I mean, these we can really and very quickly build domain adaptation, usually with much less labeled data, as the case has been for us in building our existing models, which is always a challenge in healthcare to find that labeled data or just to kind of curate that information. And as we build this capability, we believe we can support a 10x growth in the amount of breadth and depth of the capabilities that we can bring in this domain. Let me share some exciting, I mean, there are three big areas in foundation model where it's been sort of recent development that as they pertain to the medical field. As you know, large language models, I mean, for the most part, they're that language. I mean, it's really specific to text. Very limited applications right now in medical imaging specifically. So computer vision, albeit lesser extent, still is very exciting to see some of the recent work. In this work, this segment, anything model or SAM, the goal for the builders of these models were for particularly for image segmentation. I mean, they're fairly powerful AI models that can segment any object in an image or a video with fairly high quality and efficiency. And all you have to do is here you can just draw a box around, say, a person's face, and the segment anything model can really generate a mask of the face. I mean, it has been trained on a massive data set of about 11 million images and almost 1.1 billion masks, which is the largest segmentation data set to date. And this data set covers a wide array of objects, such as animals, plants, vehicles, furniture, you name it. And the ability for these to segment any object in the image is at a bar that's never been seen before. and thanks to its generalizability, ability, and the data diversity that's being trained on. And recently, we've seen segmentation performance that appears to be better for well-circumscribed objects, like with prompts that are fairly less ambiguous. We've seen this, like, for example, in pathology. However, has performed poorer in various other scenarios, such as segmentation of brain tumors. Or in our case, for example, when we're trying to look at the delineation between the white matter and the gray matter in the brain. So, which is quite common in medical domain. So MedSam explored, to further explore the idea of fine-tuning of SAM, a medical data set, and found that the performance can be significantly improved after fine-tuning. So that's sort of the latest iteration there. Sorry, the slides here were a little bit out of order. So then there's a new direction that this came out of Google Remedi's paper. I mean, and they use a combination of natural non-medical imaging as the foundation, and then unlabeled medical images to develop strong medical image foundation model. So in pre-training strategy for Remedis, it consists of 2 steps. First step involves supervised representation learning on large-scale data sets of labeled national images, basically pulled from ImageNet or from JFT. And then the second step involves now intermediate self-supervised learning, which does not require any labels at all, and instead train a model to learn medical data representations on its own. And this has demonstrated two abilities. The first, I mean, improvement in the zero-shot generalization to out-of-distribution settings, or OOD, with zero access to training data set that has shown to be quite of high accuracy, and then a significant reduction in the need to annotate the data in the out-of-distribution settings to reach performance equivalent to clinical experts or even thresholds demonstrating clinical utility. I mean, just a note here, I mean, it's also has shown, Remedies has shown in distribution performance up to 11.5% relative to improvement diagnostic accuracy over even strongly supervised baseline. So there's absolutely quite a bit of promise in this approach. The third really exciting model is we've seen recently with MedPalm and MedPalm 2 specifically, which is another medical foundation model that's built on top of 540 billion parameters that uses instruction tuning, medical data fine-tuning, as well as better prompting strategy. And this model has achieved a new state-of-the-art for MedMCQ, a data set, which is the medical sort of entrance exam, and human evaluation of the output, which is in the long-form answers to consumer medical questions, has shown that MedPalm 2 answers were preferred to physicians, and also answers cross 8 of the 9 axes relevant to clinical utility, has also shown high performance, such as factuality, medical reasoning, capability, and low likelihood of harm, but also has shown higher level of empathy compared to clinicians. And this can be a significant step to help physicians also have access to most relevant information as a search or search engine or even a chatbot in the clinical practice. Let me share with you a few use cases or applications in healthcare and how we also, like, these are some of the things that we're also working on. I mean, one example is, of course, when you look at the volume of medical images around the world today, I mean, GE healthcare equipment generate probably about 60% medical data around the world. The majority of that is medical imaging and monitoring. So I mean, this space has accelerated over the past decade with almost 5.5 billion studies generated every year around the globe by a shrinking number of radiologists. And it can be fairly difficult to structure this information, in which it takes many of our customers weeks or even months just to kind of be able to structure and analyze an index in order to build or derive insights from this data. And here's how Gen AI can really help us structure this information and relieve the burden on an overstretched healthcare workers. I mean, taking a patient's entire medical history, for example, for the last 10 years, I mean, Gen AI can help radiologists create a combined report from all the prior findings and then be able to summarize the progression of a tumor over the same period, associating current and prior medical images study, radiology reports, lab results, and even genetic information, and then be able to generate even a summary for in layman terms for the patient, or summary report to the surgeon or specialist who commissioned the imaging study. I mean, all from the same set of information, and then be able to even help the radiologist generate a really rich report with all the measurements in a hyperlink format. And this sort of bidirectionality between text and imaging, you can see that how all that can happen in a fairly interactive, self-supervised way, where radiologists can just kind of intervene where they need to, or just to kind of edit the output. And in this case, we see, for example, a nodule in left upper lobe periphery, size 5 millimeters in 2013, 6 millimeters in 2018, and then almost the same size 2023, essentially unchanged. So the imaging characteristic of this summary report point toward a more of a benign finding. So instead of here is building and maintaining hundreds of models for each of these tasks, as the case it is today, I mean, here we have one large model that serving multiple purposes for different kind of personas and seamlessly integrated multimodal data, both structured and unstructured, interacting bidirectionally between the images and the text and many other modalities, and also easily can integrate with radiologist and clinician workflow. Another example is large language models to track care pathway and recommend next steps in a treatment based on medical guidelines. I mean, medical guidelines, these are driven by, drive most of our diagnostic decisions, and it can be fairly laborious to kind of scan through. Yes?
I had a question on the previous slide. I don't know, are you taking questions now or at the end?
We're doing a keynote, and then we can take questions. Okay, thanks. Right, so how can you optimize patient care based on these guidelines? So they can be fairly complex documents that define care pathways, including many alternatives that depend on the patient characteristics, their history, and also where they are in the care pathway. So when followed consistently, I mean, these care pathways can potentially improve patient outcomes and quality of care substantially, and other areas in diagnostics and screening that large models can really help with these guidelines. Here's an example where Dr. Clifford Sturmer, a rheumatologist in the US, who uses ChatGPT basically to deal with insurance denials. So usually he sits down, writes a letter, puts references, spends about 2 or 3 hours just kind of going through this process, and then sends that to the insurance company to describe why his patient needs a certain test. And oftentimes this is a fairly adjudicated process, back and forth, and many other documentation. And now he uses ChatGPT just to write those letters. I mean, automatically draft the replies to patient messages. And we've seen recently, like with Microsoft, OpenAI, partnering with Epic, about how they can, specific use case around how can you communicate directly with patients with Gen AI, general questions, instead of needing data scientists to query specific data, and then be able just to kind of draft a reply automatically to patients as they interact with their care. Another example is virtual assistant to aid patients in managing their health. I mean, patients having a dialogue with his digital health history. Here specifically, Varun connected ChatGPT directly to his personal health on his iPhone, and now he can have a conversation about his entire 2-week worth of history, which right now is limited to few data types like step count, exercise minutes, active energy burnout, and sleep, and so on. But you can imagine that, like how a future that you can actually track all your data in a private first manner, understand unique needs, and offer more tailored advice based on your personal health journey. And ultimately, you can ask questions like, my leg is cramping, what would you recommend is causing it? Or I'm training for half a marathon, can you create a training plan for me? or what can be my last, what was my last cholesterol level? Is it too high, too low? What can I do about it? And that sort of interactions. You can see a quick demo here about how some of that is in action. Okay, so I mean, in the pursuit of ethical AI, especially in healthcare, I mean, this is really crucial to prioritize data privacy, minimize bias, ensure rigorous validation, and uphold these principles in order to lead to safe, accurate, and equitable healthcare outcomes for all. I mean, addressing specifically AI bias requires a holistic approach of technical advancements, as well as ethical considerations and regulatory involvement and measures. And FDA is looking to partner with medtech and big tech companies on regulating AI. And if we look specifically about responsible AI, I mean, the great thing is over the last few years, I mean, we've made big strides in understanding the challenges and gaps in the space, and things definitely have improved a lot, but the problem is nowhere near solved. I mean, the area is one of those where interpretable and explainable AI becomes particularly important in breaking the black box, especially in the form of readily usable tools and diagnostics that we can use to get insights into the model's inferences process in order to better understand how the output was sort of derived, and in order to improve its performance and ensuring that there's always a human in the loop. Addressing AI bias requires also a holistic approach, as I mentioned, to bring all parties together. And we really call on collaborations across all sectors and stakeholders to be able to develop an environment that ensures the responsible use of these technologies. They're really wonderful technologies if they put into for the right use, because they will drive efficiency and improve efficacy, protect privacy, promote equity and closing gaps in care, but also support data and derive interoperability of a future healthcare. And together we can truly build a more flexible health system and imagine a future where healthcare has no limits. And with that, I'm happy to have a chat with Kurt and take it from there.
Thank you so much.
Thank you.
Taha. That was very interesting, compelling vision for the future of AI. We've been getting a couple of questions from Slido, and I understand there is one in the room as well. I guess the first question that we heard about is replace versus assist medical professionals. You showed us a lot of examples there. Can you just give us a perspective of how GE thinks about that question of replacing versus assisting caregivers?
Yeah, no, this is a really great question, and we get that a lot. I mean, we look at AI as a truly assistive tool. It's not to replace. It may replace functions, automate parts of the boring parts or the manual parts of, say, a workflow is a perfect example of that. Where, I mean, I just mentioned, or I just showed the example about how radiologists can waste 3 hours of their time just kind of delineating organs. And if you have an assistive tool that can help you do that in less than 20 minutes, and do that accurately, do that in a way that's consistent, cross patients in the same patients, reproducible across different modalities and planes, why not leverage that, right? I mean, almost like you think about it as, I'm an interventional cardiologist, and you think of a lot of assistive tools that can help you in a way, but imagine like what the stethoscope has done to the field of medicine over the last 250 years. And we almost think about it the same way. So this is an intelligent tool in a toolbox that the more that you care for it, the more you can give it feedback, the more it's adapting to your need. But it's very also important that you do that in a responsible way, understanding really it's not magic. You need to understand what's the input and understand what's the output. And it's up to us here in society to do everything we can to break the black box to really understand how the output and the inferences were made in the first place.
Great, thank you. Was there a question in the room at some point here? I think there was. No? You good? You got it answered? Wonderful. I want to make sure you have such an interesting background, having gone from academics to government and then to industry. Well, let's start with kind of the academics to industry transition. Can you tell us a little bit about how you made that decision? We have this vast AI ecosystem. All of those institutions are really important. But how did you think about that choice?
Yeah, tell you about a company I worked for before joining GE Healthcare. I mean, for 5.5, 6 years, I was vice president of machine learning at Amazon and chief medical officer. And it was, if you look at Amazon invented the cloud, and that's Amazon Web Services, over 16, now 17 years ago. And if you look, I do have a Master of Science in Biostatistics and Machine Learning, and it's really near and dear to my heart about how we can leverage data and population health data to really drive a lot of decisions that we make. But it's fairly important. Honestly, those lines are getting more very blurred right now. Is about innovation can come from anywhere, and if we really want to take that to scale, oftentimes we look at massive sort of inflection points that can happen anywhere in industry to really be able then to translate that to our domain. And in this case, almost all large models, those are things were born in the cloud. Machine learning at scale is born in the cloud, and you need that high computation power, but also more interactions, like consumer interactions. Amazon was using has been using machine learning since early days to personalize your journey. We're talking about huge sparse matrix of billions of products and trying to personalize the one item for you and then search in a real messy data about how we can find that. If you look at our health data, 97% of our data in healthcare is unstructured. That's medical images, that's a report, that's a genetic mutation that can be mentioned somewhere, the EKG trace, etc. So there's a lot to be borrowed from those innovation in those industries to really kind of bring forward that fold. And honestly, it's back in 2009, the General Obama administration was around H1N1 was how can you scale in the middle of H1N1 surveillance, where CDC had coverage about 8% emergency rooms in the US, and how do you scale that to in 8 weeks before the second wave of the pandemic to cover 90% of the population? And it was a really massive effort that I needed to lean more on public health departments, but I needed a technology platform to help me do that. And in 2009, there's not a single health department could scale at that massive scale, not even the largest data center in the US at CDC. And this is where I partnered with AWS back in 2009 to how can we do this securely and in the most private way to work directly with hospitals and labs to cover about 320 million population in the US. So you can imagine that scale where they built for those scales for consumer products and startups and that sort of thing, where it was almost a great partnership to really kind of leverage all these tools for us to serve that purpose.
And when you were in government, I imagine that because it's the government, you have some ability to gather data from hospitals, for example, for H1N1, public health, and so forth. As you move to industry, how do you think about that problem of access to health data, because it's really being produced primarily by health care delivery organizations and academic medical centers and the like. So how do you think about
Yeah.
the need for data when you're developing these innovations like you showed today?
Absolutely, and this is really, again, you lean on a lot of partnerships. I mean, even in my world today with GE Healthcare, we work very collaboratively with institutions like Stanford about how can we bring the technologies, innovation in an MR and a CT, and bring our breadth and depth also about how these can be brought to scale with advancements in Gen AI or deep learning, and how can we apply them together. And it's that partnership that helps us kind of push the envelope and bring the right technology to solve the right problems. But for us, it's always been about working backward from those concrete problems and use cases to help solve for those. And one of the things is, like, unlike images of dogs and cats on the internet, where you can build any like amazing models or like access to largest Wikipedia in the world and build these really amazing large language models. I mean, healthcare data is fairly private, and as I mentioned earlier, is large volume of that is unstructured and not curated. So to find high quality data is, I believe, that the innovations that we're seeing right now with Gen AI is going to really help that quite a bit there, because it can take us much of the way where we're spending a lot of time today about curating and a lot of this information, so that way we can do them at a different scale as we have been all along.
Yes.
So thank you for an excellent presentation.
Thank you.
I have two concerns. One is transparency. When you give answers, no references, no citations, no way to check. And two, how do you keep up to date, or how up to date do you keep? For example, you say we're going to give recommendations based on guidelines. Guidelines change. For example, several years ago, we dropped the age of screening for colon cancer to 45. Now recently,
That's right.
maybe in the next few days, we're going to drop mammograms from 50 to 40.
Yeah.
Are you incorporating on a daily basis, weekly basis, monthly basis, new information so that you can give up-to-date answers?
So, I mean, from our world in medical imaging and how we're distilling these algorithms, for example, AirX brain that can really segment the organ, many planes, and also prescribe the slices. We have a feedback loop when the algorithm is not doing right, is where you can correct that, and then kind of the cycle starts anew. So, I mean, the example I mentioned about the guidelines is these are the power of these technologies can really help you summarize a lot of that information in a most concise way. But if you remove the human from the loop, or you move the expert from the loop, or the content is not updated, almost like the data now start decaying, then these models are not going to perform as well in the wild. So benchmarking, having feedback in the loop are super important about how you deploy these models in the wild.
And what?
This is based on data that's 2 years old.
Absolutely.
Because that's not being done, and I have patients who go online, they say, well, it says on this that you disagree, and I said, well, yeah, that's based on data. Microsoft is using data from 2021.
I mean, that's the challenge you see right now with a lot of these public tools, the way they're deployed, and that lack of referenceability. Where did you get this answer from? And this is back to my early comment. Like, it's starting to break the black box. It's very important by understanding what went in the model, what should have gone in the model in the first place. I mean, bias is one aspect of this. But there are many other aspects that by breaking the black box, you can really start understanding that. And I spent much of my career also like working really hard on this particular problem. I mean, back in the days in the 90s, I mean, you build a neural net, and that was like 6 layers, and now like, I mean, that's a joke, right? I mean, it's talking about hundreds of thousands of layers in between. So how do you know really what went in the model in the first place? It's very important that you kind of reverse engineer all this process and have full transparency to what went into those models.
Part of Daniel's question also, I think, relates to something that came through Slido, and that is, what are the benchmarks? And I imagine you're thinking about this because I know in the market, customers of AI algorithms are asking the question, well, how do I know this is going to work for my patients.
Absolutely.
How do you help answer that question as you think about these?
Yeah, I mean, again, in our world in GE Healthcare, we work very, very closely with physicians and clinicians and radiologists and technicians that are constantly giving us feedback on how the algorithm is working and how we refine and fine-tune this algorithm. And then as you deploy the models, that beyond their clearance and FDA clearance or ICE or CE mark is now is in the hands of tens of millions of patients or affecting tens of millions of patients. Definitely, we see that how these models are behaving differently. So keeping that feedback loop is very, very, very important. Especially there is no such benchmark that exists today in the market, and we're working very closely with our regulatory agencies like FDA and especially in the world of Gen AI is what are the best ways about how to deploy these models, to benchmark those models. I mean, similar when I was in FDA with Precision FDA with Rob Califf, I mean, we established Precision FDA for the fact that there existed nothing in the world around benchmarking next generation sequencing technologies. Like, how would you know that your algorithms that call in a variant is accurate and it's reproducible? If I got an F1 score of 0.7, how do you know that's good or that's bad? And you also don't want to kill innovation because in some areas, 0.7 is amazing. It's awesome. I mean, in other areas, if everybody else is getting 0.99, then it's a black and white. You should not consider and should have that full transparency in the world. Today, that lens of consumer report does not exist, especially in AI or in our world, specifically in healthcare. And we need to just kind of continue working together as a community and educate the regulatory agencies about how best to benchmark this field.
Time for one more. Oh, yes, Forrest.
Good morning. I'm a clinical radiologist working in the largest healthcare system in the United States, the VA healthcare system. And I wanted to share with everybody in the audience and with yourself the challenges we have as clinicians getting AI adopted. There's some of us that feel that the AI tools we've implemented in our practice makes us better radiologists. There are others that do not even want to try to implement it. So what are your thoughts about the challenges in the real world of getting clinicians comfortable with adoption and implementation?
Yeah, no, that's a really great question. And it also depends on, are we talking about operation efficiency, or are we talking about clinical validity? I mean, and those can be clinical-based. Yeah. Pixel-based, yeah. I mean, it's oftentimes you can't change culture overnight. But like things we're seeing that really taking a lot of adoption is things when it comes to advanced visualizations and 3D post-processing. Those take a lot of time, and automating a lot of those and are definitely things are of great value to clinicians, especially radiologists. Automated measurements, especially how can you reconstruct a 3D from 2D images and then be able to do the accurate measurements and have that as an adjudicated process. If you don't agree with it, you can also give a feedback. Given that feedback loop, especially like we do that today in ultrasound, we can automate most of this stuff, but it's a guided workflow. Here's the next step. Did I get this right? You can press yes, you can press no. And that sort of feedback loop gives you a far more like a Tinder-like experience that you actually feel you're part of designing the system, and then lean on clinicians to actually design these systems in the first place rather than just kind of pushing the technology out. This is why our advanced visualization is propagated around the world. I mean, for the last 3 decades that GE Healthcare has been doing, because we're working backward from those. But for our machine learning in the last decade, especially around since COVID, I mean, almost like a hockey stick of the adoption of those, because it's solving pain point and heavy lift, rather than here's a nice thing that I can add on top, or I detected this, or I was able to predict this and that sort of thing. I mean, really, it comes down to removing the heavy lifts in the process, and oftentimes that's around the workflow and workflow optimization.
Taha, it's the top of the hour. Thank you so much for sharing your thoughts with us in your presentation and the conversation. Thank you. We have a 10-minute break, and we'll be back right here with the next session in 10 minutes. Thank you all.